I've got this piecewise function, which I've typed into Mathematica as f of u equals 2 if u is between 0 and 3, and negative u plus 5 if u is between 3 and 8. Why am I using a letter u? Because it's going to be a dummy variable for an integral. That's why. Not that I have to use a u, I could use a t. What does the graph of this function look like? If I call the horizontal axis u to be consistent, it's horizontal at 2 when u goes between 0 and 3. Let's say 3 is right there. And it's got a slope of -1 and a y-intercept of 5 when u is bigger than 3. Notice if you plug in u equals 3 into this, you get -3 plus 5, you get 2, matching the value at u equals 3. This is a continuous graph, is what I'm trying to say. The slope is -1, so this intercept right there is going to be 5, but we go out to u equals 8 here. And the value at u equals 8, -8 plus 5 is -3. You could pretend, if you like, that this is the velocity of some object moving along a number line back and forth. I didn't label it as a velocity, but you could pretend it is. Because we are going to integrate this. We are going to think about, in that application at least, a displacement, change in position. If this were a flow rate, telling you how fast water is going in and out of the tank, it's going in when it's positive and out when it's negative, integrating it would give you the change in volume. What I want to illustrate here is that you can think about the fundamental theorem of calculus with a variable in the upper limit of integration, even with piecewise examples, and even if you don't start the lower limit at 0. Even if I start the lower limit somewhere else, and in this picture that I got in Mathematica, I'm starting the lower limit at 2. What I'd like to do is create a function capital F of x by doing this integral. Capital F of x changing to x here, though I could use t, is the integral of little f of u, not as an indefinite integral, but as a definite integral. I'm picking a lower limit of 2. Why? Just because I feel like it. I'm serious. Just to illustrate, you can do something other than 0. I could have picked 1. I could have picked 1.5. I could have picked pi. It doesn't matter what you pick for the lower limit of integration. I'm going to pick a 2. It really doesn't matter. If I do pick a different number, I will get a different function. But no matter what number I pick for that lower limit, I will get an antiderivative of little f. That's the point. I make this upper limit a variable x. And I'd like to know, what is this equal? I hope it's pretty intuitive, since little f is a piecewise function, that probably this is going to be a piecewise function too. And that will be true. What I'd like to do to make the concept hit home that this is going to be an antiderivative is I'd like to find this integral for different cases, for different values of x, purely by thinking about areas, not by using or thinking about antiderivatives ahead of time. How do I do that? Think about cases. So here's 2 right here. What does this integral equal? In case 1, x is between 2 and 3. Why is that case 1? Because if x is between 2 and 3, then the integral is the area of this rectangle that I'm drawing right now. Area of a rectangle is base times height. Base times height. For that rectangle, The base is not x, it's x minus 2, right? The distance between x and 2. What's the height? It's 2. The area of that rectangle, if I pretend x is some fixed number between 2 and 3, is x minus 2 times 2, which is 2x minus 4, which has a derivative equal to 2. Hey, that's not an accident. It also happens to equal 0 when x is 2. Hey, that's not an accident. I'm starting my integral at 2. The integral from 2 to 2 is 0. Next case, case 2. This is essentially the content of section 6.1 that I'm doing right now. It's called constructing antiderivatives graphically. Case 2, I redraw the graph of little f. But now, let's pretend x is between 3 and 5. Why between 3 and 5? Because then I'll have to figure out the area of a trapezoid, well, a shape like this that I'm drawing right now, which is a rectangle and a trapezoid, if you break it into 2 pieces. Can you see that? Is that big enough? This blue shaded region that I probably should have drawn bigger is made up of a rectangle over here on the left and a trapezoid on the right. The integral still gives you the area. Capital F of x in this case is base times height for that rectangle plus the area of the trapezoid there, which is the base times the average of the heights. The trapezoid has 2 heights, one on the left and one on the right. Let me draw the picture a little bit bigger here. Yeah. Sorry. This is the picture. This is 2, this is 3. This is 2 up here. This is x here. The base of the rectangle is 1. Its height is 2. The base of the trapezoid is x minus 3. What's the average of its heights? Well, this height is 2. What's this height? It depends on x, doesn't it? It depends on little f of u. It's negative x plus 5, actually. Or 5 minus x if you prefer. That's a positive number, right? If x is less than 5. Averaging 2 numbers means add them and divide by 2. That's what I'm doing. Simplify. What do I get? This becomes a 7 minus x. If I divide that by 2, well, maybe I should put the divide by 2 as a 1/2 out in front, like that. Continue simplifying. FOIL this out. First times first is 7x. It's a little weird here because I got the minus x over there. Outside times outside is minus x squared. Inside times inside is minus 21. Last times last is plus 3x. That is the same as negative x squared plus 10x minus 21. If I multiply that by 1/2, then I get 2 minus 1/2 x squared plus 5x minus 21/2, which simplifies to negative 1/2 x squared plus 5x. 2 minus 21/2 would be negative 17/2, I think. Whoa, that seemed like a lot of work for what do we gain? Well, we did get the right formula, hopefully. And I am encouraged because I do see that the derivative of this would be what? Negative x plus 5, right? That would be the derivative of that. Hey, that matches little f. if you replace u with x, negative x plus 5. Not a coincidence. These two formulas should also match up when x is 3. The integral should be a continuous function here. Do they match up when x is 3? The value of this when x is 3 is 6 minus 4 is 2. The value of this when x is 3 should also be 2. Let's see. 3 squared is 9. Negative 9 halves. Minus 17 halves is what? Negative 26 halves, which is negative 13. 5 times 3 is 15. 15 minus, what did I say, 13? Is 2. Hey! It's right. It's not just a curiosity. This is fundamental. Let's try case 3. What's case 3? How about x is bigger than 3? What's the picture? Draw a bit bigger this time. I meant bigger than 5, sorry. Bigger than 5. Like right here. The integral still starts at 2 and gives us this area, but then we have to subtract that area. Capital F of x is going to be the area right there minus that area. Hey, that's a sideways trapezoid of height 2. What's the average of its lengths? This one is 1. This one is 3. That trapezoid has area 2 times the average of 1 and 3. That's a 2. 2 times 2 is 4, is the area of that trapezoid. I have to subtract the area of this triangle. 1/2 base times height. What's the base? X minus 5. What's the height? It'd be that distance, which is technically the absolute value of negative x plus 5, which if x is bigger than 5 is actually its opposite. It's x minus 5 as a positive height if x is bigger than 5. I know that was quick. So I multiply by another x minus 5. What happens when I simplify all this? You know what you should get? You should get probably the same thing as we got in case 2. Is that going to happen? Let's see. Expand this out. Distribute the negative 1/2 through. It's starting to look good. 4 is 8 halves. 8 halves minus 25 halves is negative 17 halves. I got the exact same answer as I did up there. It had to be the same answer because it's still got to have the same derivative and it's got to be a continuous graph. These have to match up. It had to be the same answer. Here's one more case. And this last case is going to also illustrate something at the end of chapter 5. Hanging with me here? Case 4, the last case, is when x is less than 2. Case 4, x is less than 2. Capital F of x is still, even in case 4, the integral from 2 to x of little f of u du. Wait a minute. How can that be? If x is less than 2, like 1.5, how can I integrate from 2 to 1.5? That's not allowed, is it? Yes, it is. But you have to know what it means. Hang with me. We are still thinking about the graph of little f. It still looks the same, like this. That's 2, this is 3, this is 5, this is 8. We are still starting the integral at a lower limit of 2 and going up to x, but now x is less than 2. Does that mean I have to figure out this area? Yes, but with a caveat. Before you figure out that area, you do need to switch the limits of integration around. And instead of going from 2 to x, go from x to 2. But if you do that, you have to put a negative sign in front of it. This is a property of integrals in section 5.4. Why? Come back to the why here in a minute. If you do that, then, for example, if x is 1.5, you're integrating from 1.5 to 2, you're finding the area of this rectangle as a positive area. Base 2 minus x and height 2. As a positive area, that's base times height, 2 minus x times 2. But the integral is negative, because you have to put the negative sign there. Simplify this. Get negative 4 plus 2x, or if you prefer, 2x minus 4. Hey, that looks familiar. Same answer as we got in case 1. Not a coincidence. We had to get the same answer. And yes, this is still a function whose derivative is 2, matching that 2 right there. We have now constructed a function, capital F, that's an antiderivative of little f. If I write capital F of x as a piecewise function in simplest form, in case 1 and case 4, we found that f of x equals 2x minus 4 if either x is less than 2 or if x is between 2 and 3, meaning if x is less than 3. And we found it was that quadratic, negative 1/2 x squared plus 5x minus 17 halves. If you like, minus 17 halves is the same as negative 8.5. If x is bigger than 3, or say between 3 and 8, since we're only allowing x to go up to 8. And we could graph this function. And what would the graph look like? It does have a value of 0 when x is 2. Plug in x equals 2. 2 times 2 minus 4 is 4 minus 4 is 0. Because we were integrating from 2 to 2. The integral, that's another property of integrals. Then the integral of a function from a to a is 0. There's no area under the curve. The rest of the graph looks about like this. The slope here is 2, so this has to be negative 4. It has to continue going up with the slope of 2 until you get to x equals 3. And this is 2 right there. And then once you reach x equals 3, the graph becomes an upside down parabola. And it turns out if you graph this parabola, it'll look about like this. Will it go down to 0 by the time I hit x equals 8? I think so. But I have to figure it out to know for sure. It'll go down and cross 0 at some point. I'm not sure if it'll be before 8 or after 8. I'd have to figure out, I'd set it equal to 0 and solve for x like with the quadratic formula. You also could think about it, is this area bigger than or smaller than this area? It looks like this area is bigger here, if I drew it right. So probably this negative contribution to the integral outweighs this positive contribution to the integral. Probably it goes negative before 8. That's what I'm guessing, but I could be wrong. My picture could be faulty, misleading. That's what I'm guessing. I've constructed a piecewise antiderivative of a piecewise function. If the original function, little f, represented a motion of velocity, what kind of motion would it be? Starting at time equals 2. That's what I'm pretending since the lower limit is 2. Why time equals 2? Just because I feel like it. Right? It could be 2 o'clock on the dot or something. This time could be in hours. T equals 0 could correspond to noon. You're traveling with a positive constant velocity to the right, say, positive, for a little while. Then the velocity goes down linearly to 0 when t equals 5. That means the object is slowing down as it continues moving to the right. Once you reach t equals 5, it turns around and it becomes a negative velocity. So now it's moving to the left. And because it's going down further and further, it's actually speeding up as it moves to the left. And probably, just like I was guessing, this graph goes negative before you reach 8. In the end, probably you end up to the left of where you started with a negative displacement. Probably. What does the time from 0 to 2 correspond to? That corresponds to time before time 2, the past. You were moving with a constant velocity still to the right from time 0 to time 2. You just didn't start the clock thinking about the clock until time 2. The fact that when in case 4, we had to switch these limits of integration around and put a negative sign in front of it corresponds to this. Imagine videotaping the motion. So you got it on video. Now imagine running the video backwards. The integral from 2 to x when x is less than 2 is like figuring out the change in position if you run time backwards, like watching the video in reverse. Now, you were traveling to the right that entire time, but if you watch it in reverse, you're traveling to the left. So what this is saying is, in reverse time, if you let time run backwards, your change in position is actually negative. That's what it's saying. That's why you have to put that. That's why it makes sense to switch them around and put a minus in. Because when you run time backwards, for that application at least, when you run time backwards, your change in position is the opposite of the change in position when you run times forwards. This was harder to talk about 100 years ago, or even 50 years ago, before people could watch videos backwards. I guess even 50 years ago they could. They'd seen those old reels. You could put reels on projectors. You could run them backwards, I guess, probably. So, okay, before 100 years ago, people had a hard time imagining watching things run in backward time. But you can literally watch it on video now. People are walking backwards, right? Instead of forwards.